All right, this is it. This is our last topic, last new topic that we need to cover for this course, the derivatives of exponential functions. And we've already done, remember, a little bit on it, because we know how to take the derivative of a function as long as it's e to the x. Derivative of e to the x is e to the x, so that part works out fine. The problem for us is what to do if it isn't a base of e. So in the last class, or last lesson, I guess I should say, I asked you to look at these and try and evaluate expressions like this. I can't remember what numbers I put in. But what I wanted you to notice, I hope, is as you let h get closer and closer to 0, this limit approaches the value of ln 7. Okay, so the values are approaching the same thing. And that's going to be important for us. It means that I have this, if I have this, notice same form, right? The limit as h approaches 0 of b to the h minus 1 over h. That approaches ln of b. Approaches ln of b. And we're going to need that. We're going to need that in order to get derivatives of exponential functions with different bases. So, if f of x equals b to the x, and that b can be anything now, determine f prime of x using first principles. So good, really good. Last day of calculus, and we get to do a little bit of first principles again. So f prime of x using first principles was the limit as h approaches 0 of f of x plus h minus f of x all over h. And remember, that was called our difference quotient. All we were doing there was finding the slope of a secant, right? Pick a particular value of x and then move a little bit past it. That would give you the secant. But by letting h approach 0, that secant is getting closer and closer and closer to our tangent. And that's how this worked. Now our function is b to the power of x. So as we're taking this derivative, f of x plus h would be b to the x plus h minus b to the x all over h. Right? Still using first principles here. That's what it would look like. F of x plus h means wherever I see an x, replace it with x plus h. Now with limits, the hope is that you would just be able to sub in the h as 0, right? But if we did, you'd get a 0 on the bottom. On the top, you'd get that x plus h would just become x, right? So b to the x minus b to the x, which is another 0. So you get 0 over 0, which we said was our indeterminate form. And then we're into trouble. That doesn't mean anything for us. So we need to come up with some way of simplifying this. And we can do that, actually, by taking advantage of some exponent stuff that we know. Let me remind you of something. If we have this, x to the 3 times x to the 5, we're used to simplifying that and writing it as x to the 8, right? But technically that's x to the 3 plus 5. So what we have here is similar. I have b to the x plus h. So I'm going to go backwards. I'm going to go from this part to this part, which is weird. That's not the way we usually handle exponents. We like to simplify things, put them into one. Now I'm going to split it up. But I can write this as b to the x times b to the h. Minus b to the x is still kicking around at the end, all over h. Okay, that's just exponent rule stuff that I'm allowed to do that. And the reason that turns out to be a good idea is there's a b to the x, and here I have a b to the x at the end. So if I common factor that out, the limit as h approaches 0 of b to the x times b to the h minus 1 over h. Right? I've pulled that b to the x out of the way. So this part right here would be left with that minus 1. Now we've had to worry about limit rules before, and it's the same case here. We have the product of two things, and so I'm allowed to take the limit of each piece. So I'm going to take the limit of b to the x and multiply that by the limit of this fraction. And this is kind of neat actually, because at this point, oops, that's a really bad equal sign. This first bracket, the limit as h approaches 0 of b to the x. B to the x has nothing to do with h. So the fact that we're letting h approach 0 doesn't matter. So that's just b to the x, right? Let h approach 0, that's fine. It's still going to be b to the x. But the second part, the limit as h approaches 0 of b to the h minus 1 over h, we just wrote that down, right? That was this. That's equal to ln b. So this second bracket is just ln b. And that's our derivative. That's f prime of x. So if we start with an exponential function, that's how we calculate it. And notice I've changed the order there a little bit. We usually write the ln b first, because b was the base, right? B is just a number. I did this in general for any base, but b is just a number. So ln of b is also a number. It's a constant out front, whereas the b to the x has our variable part to it. So if we put those two parts together, the ln b to the x, that's going to give us derivatives for exponential functions with different bases. And that's what we want to practice with. So can we take a couple of derivatives here? 10 to the x, this is our, I suppose, most straightforward exponential function. The way we're supposed to do it, it's not a base of e. So it said take the ln of the base, so ln of 10, times b to the x, which in this case is just 10 to the x again. That's the derivative. Okay, so not hard, it's a quick little one, but that's the rule that we found for being able to take the derivative of an exponential function. Similarly with this one, the base is 2, so ln 2 goes in front, and everything stays the same at the end. The brackets are probably a little bit better than the way I did it in the red there, just to indicate you do ln 2 separately, you do 2 to the x separately. And this is kind of a weird one to throw in, because we knew this one already, right? If f of x is e to the x, then we knew the derivative of that is e to the x again. That was the very first thing the first derivative we were able to do in this unit. What I want to show you is that if we use this rule, it still follows the pattern, it still works. So what we're supposed to do is take ln of the base, so that would be ln of e, and then multiply that by the original function, e to the x again. But ln of e is just 1, so you just get e to the x anyway, which we knew was going to happen. But I just wanted you to see that following this rule still works in this case. Okay. So now we have to start making these a little bit more complicated. There's a constant in front. Well, that's not a big deal, because all along we've had to deal with constants in front. And we know that when we take the derivative, the constant just stays there. So the 13 stays. And then the derivative of 10 to the x was ln 10 times 10 to the x. So a constant in front isn't really a big problem. This one's a little bit harder, because now we're into chain rule stuff again. It's 7 to the power of 4x. So the chain rule says do the derivative of the outside times the derivative of the inside. The derivative of the outside is that 7 to the x function. So the derivative of that would be ln of 7, right, ln of the base, times the same exponential function, so still times 7 to the power of 4x. But then we still, that's the derivative of the outside, right? We still have to do the derivative of the inside, and the inside part is that 4x. So the derivative of that would be 4. Put this down here maybe. This one isn't too bad, but I wanted you to see how the product rule would kick in. It's 5x squared times 4 to the x. So it's a function times a function. Product rule says the derivative of the first, which is just 10x, times the second plus the derivative of the second. This is the new part. The derivative of the second would be ln 4 times 4 to the x, right? Derivative of that one, ln of the base times the function again. That's derivative of the second times the first function, which was just 5x squared. So that's how we're using the product rule to get the derivative in that case. And here's the last one, just for kicks. We've got a trigonometric inside of an exponential. So there's quite a bit of chain rule going on here. And we have to worry about the trig derivative and the exponential derivative all at the same time. So we can get it, but just be careful. And I think you'll see a few of these examples in practice questions too, where all it is just a case of being really careful as you're taking the derivative. It's almost like our chapter, was our second chapter test in calculus, the first page was just take the derivative of things, right? And it got complicated when I started making the function bigger. With these ones, it doesn't have to be a whole lot bigger to still be more complicated because the chain rule kicks in so easily with the exponential functions and the trigonometric functions. So the derivative of this, well, the base function is 6 to the power of something. So we start as ln 6, right? And then it was leave the exponential function exactly the same. So 6 cos 5x. That's the derivative of the outside. Now we have to do the inside. And the inside function is cos 5x. And the derivative of cos 5x, derivative of cos is minus sine, right? The 5x should stay. And then you have to do the derivative of what's inside that. And the derivative of 5x is 5. So an extra chain rule to work all your way through there. Now we just want to try a couple different problems just to make sure we're okay with what these would look like in an exponential situation. Find the equation of the tangent line. Def of x equals 3 e to the x when x is equal to ln 4. So we're shooting for this, right? We're shooting for y equals mx plus b. Remembering from trigonometry, doing a tangent line problem, there's no guarantees that this will work out nicely. So we'll see what happens. We're going to need the derivative, though, for sure. F prime of x. F prime of x is easy, actually, because it's 3 e to the x. So the derivative is just the same. The constant stays, and the derivative of e to the x is e to the x. We want the slope when x is equal to ln of 4. So that's 3e ln 4. And you can put that in the calculator again, but remember we had talked about that last class. The rule of e to the ln 4 was just 4. So that's 3 times 4, which is 12. So our slope is just 12, which is nice, way better than trigonometry, right? Nice answer for once. The other thing we need is the whole point, and we don't have the whole point, we just have that x is equal to ln 4. So if I do f of ln 4, well, that's also 3e to the ln 4. It's exactly the same as the derivative, so that's okay, that's just 12 as well. So our point is ln 4 comma 12. And so our equation, y equals mx plus b, we can put the slope in as 12. And then we'll sub the point in. So 12 here equals 12 ln 4 plus b. And that just takes one step to rearrange it and get the b by itself. Almost had enough space too. So our final answer was y equals 12x, and then the y-intercept, which is 12 minus 12 ln 4, a lot of 12s. Slope here, y-intercept there. Okay? So we can still do tangent line problems. this was how we started in this chapter, right? We looked at this little sketchpad file, and we were comparing the original function with the derivative, and then we were looking at the ratio. And what we found was we knew the derivative was always exponential. We knew that it was above the original function if the base was bigger than e. We knew that it was below the original function if the base was less than e. But we never knew exactly where this point was. Right? We didn't know that part. But now we do. Now we do. Because if our function is b to the x, if that's our function, then our derivative was ln of b to the x. And so our ratio, we called the ratio g of x, right? G of x was the derivative divided by the original function. Well, that's ln b times b to the x over the original function was b to the x. That's just ln b. So all along that y-intercept, the equation of that horizontal line was g of x equals ln b, which we didn't know at the time. But that was what was happening. And I guess to think about that a little bit, we said if b was e, right, if the base was e, then the derivative was exactly the same as the original function. The ratio would have gone right through 1 because ln of e is 1. And if the base, if b is bigger than e, then ln of b would be bigger than 1, right? If the base is less than e, ln of b would be less than 1. And that was why we saw the ratio drop below. Last question of the year. Identify the local extrema, so local max and mins, of the function f of x equals x squared e to the x. So this is kind of like a curve sketching, but all we're going to do is find max and mins. I've got the graph there, so we'll take a peek at it once we're done. We're trying to figure out where the max and mins would occur on this graph. So to find max and mins, what we do is we take our derivative, set it to 0, and solve. So the derivative of this, it's an exponential e to the x, but with a quadratic x squared. It's product rule, right? Something times something. Derivative of the first is 2x times the second function, which is e to the x, plus the derivative of the second function is still just e to the x times the first function, which is x squared. So there's our derivative. I'm going to rearrange it just a tiny bit because I'm just going to make it easier for us to see. And write it like that. So we have our derivative. If we're trying to find maxes and mins, we're going to set it to 0. So there's our equation. Can we solve it? Well, usually the best bet when you're trying to solve these equations is to try and factor things, and there's a whole bunch that's in common. Each term has an e to the x, and each term has an x in it. So I'm going to factor out an x and an e to the x. And what's that going to leave me with? I think it leaves me with 2 from the first bracket plus just x. Right? Does that look right? Yeah, that's pretty good. So that technically is 3 things being multiplied together. Right? 3 different functions being multiplied together. And so there's 3 different things we need to consider for solving this equation. Number 1 is we might have x equals 0. Number 2 is we might have e to the x equals 0. And number 3 is we might have 2 plus x equal to 0. So 3 things that might happen. This one's done for us. X equals 0 is a location of a horizontal tangent. What about the second one though? E to the x equals 0. E to the x is an exponential function, right? And we've looked at exponential functions a fair bit. We know that they have asymptotes, right? It's going to approach the x-axis but never get there. So this one we can't solve for x. There's no solutions there. So it's a candidate, it had a possibility, but as it turns out, e to the x will never be 0, no matter what we pick for x. And the last one's not too bad either. We get x equals minus 2. So that's saying for this function, there are two locations of horizontal tangents. That probably doesn't help too much. What was our original function? It was f of x equals x squared e to the x, wasn't it? So it said determine the locations of the horizontal tangents. We kind of got that. We have the x coordinates, but if we wanted to get the points too, which isn't a terrible idea, f of 0 is just 0, right? 0 squared times e to the 0. That's just 0. That's an easy one. So the origin is the location of a horizontal tangent. And the other one isn't quite as nice. F of minus 2 would be minus 2 squared times e to the minus 2, which would be 4 over e squared. I can plug that in. 4 divided by, it's about 0.54-ish. So our point is minus 2, 0.54. Those are the locations of our maxes and mins. The second one's got to be a max there, right? It's higher up, whereas 0, 0 would be our minimum. It's lower. It didn't, in this case, give us any n values. Remember, we've done n values sometimes to consider where our local extremes will have to happen as well. And here's what the graph looks like. It's kind of a neat one. There's the graph. I like it. You can see there's our max right there. There's our min right there. The reason I like it is it really takes on the characteristics of both types of graphs. On the right, you kind of get that x squared shape. Right in the middle is kind of a little bit of a combination, but you still end up with the asymptote as you go off to the left, because as x becomes a very large negative number, e to that number gets really, really close to 0. So you still end up getting the asymptote happening. And there we go. That actually wraps up all of the material for this class. So congratulations, you've now completed all that you needed to do for the calculus and vectors course. Now it's just time to do a little bit of review.